Lights, camera, action! Hi again, I'm still Jim. And as you recall, we started earlier with the early history from Gallileo to Edward Crossley and his 36-inch that he shipped to Lick Observatory. By the way, I had an opportunity to preview this presentation down at Carbondale when we were down there for the eclipse. We did several presentations. Tom Hagen did one, and I did a couple of others. And they had invited us, the Warren Astronomical Society, to become have a closer relationship with their organization down there. So who knows, in 2024, maybe. In any event, this period, starting with Hale and the modern era of telescopes, marks the beginning of the modern era of astronomy. As the 19th century ended and the technologies of photography and spectroscopy matured, it became clear to many astronomers that the future of astronomical research was to be conducted using larger reflector telescopes designed for these new tools on the top of lofty mountain peaks to maximize the collection of photons. By this time, the United States had become the world leader in astronomy. More telescopes and more astronomers, primarily exploring the new astronomy and calling for bigger and better telescopes. Driving this engine of astrophysical research was the availability of money, mostly from wealthy private donors, as government funding essentially did not exist at this time. By 1899, at Lick Observatory on Mount Hamilton, James Keeler had demonstrated the power of photography with a large reflector by refurbishing the 36-inch Crossley, built in 1879 by an English amateur, Andrew Common, and producing evidence to seriously question the nature of the mysterious spiral nebula. A close personal and professional friend of Keeler's was George Ellery Hale, who had already made his mark in astronomy by building the world's largest refractor telescope and establishing the Yerkes Observatory as, quote, the birthplace of modern astrophysics in 1897, soliciting funding from a wealthy businessman. Hale, influenced by the cosmic questions raised by Keeler, became obsessed with building larger telescopes to answer them. In 1904, he founded the Mount Wilson Observatory on top of the 5,700-foot mountain in California, using funding that he had obtained from the Carnegie Foundation. At Mount Wilson, Hale constructed the 60-inch telescope designed by George Ritchie, his chief optical engineer, in 1908. And even before its first light, he had ordered the casting of a 100-inch mirror for a much larger telescope, which was completed in 1917. Again, with funding from another wealthy private donor. Each of these largest in the world telescopes posed major technological challenges to be overcome by Hale, Ritchie, and others. Many notable discoveries were made by many famous astronomers, such as Howard Shapley, Walter Baade, Alan Sandage, using these instruments. But notably, the most famous was Edwin Hubble's discovery of the Cepheid variable in Andromeda in 1923, which greatly expanded our universe. And yet, Hale's quest for answers to the mysteries of the cosmos was not satisfied, and in 1928, he secured a grant of $6 million from the Rockefeller Foundation for the construction of a 200-inch telescope. This mind-boggling for the time technical achievement took 20 years to accomplish and was not completed until 1948, 10 years after Hale's death in 1930. It was an epic example of American technical entrepreneurialism and was to stand as a monument to Hale's nearly half-century of dynamic leadership in astrophysics. The technical and engineering aspects of building such a large and precise instrument required innovative methods and technology which were eagerly followed by the public and which led some to consider it the moonshot of the 1930s and 40s. It was the largest effective telescope in the world until 1993, or for nearly 45 years. After the dedication of the 200-inch Hale in 1948, there was an extended period during which no comparable telescope was built. Although the Russians had built a seriously flawed 238-inch instrument in 1975, it was plagued with such serious problems as to be considered unsuccessful by most experts. We'll have more about the BTA-6, the Russian telescope, a little bit later. From 1948 until the first light of Keck 1 in Hawaii in 1993, only a handful of large telescopes were built. And with the exception of the BTA-6 and the multiple mirror telescope, which we'll talk about in a little bit, all were smaller versions of the Hale. The reasons for this dearth of giant telescope building activity are many and varied, but for 30 years, between 1948 and 1978, astronomers and telescope engineers seemed to be stuck in a quagmire of indecisiveness regarding the proper road forward. Should we have many modest telescopes or a few more enhanced Hales at an estimated $100 million and 15 years to deliver? The main reason for this lack of initiative toward bigger instruments had to do with politics and personalities. One faction, represented by noted astronomer Jesse Greenstein, advocated that U.S. astronomy research should be privately controlled by elite universities, supported by wealthy benefactors such as Caltech and Carnegie, and with a relatively few autonomous observers as practiced for the first half of the 20th century at Mt Palomar, Mount Wilson, and Lick, with Hubble, Keeler, and Curtis. The other faction, led by Leo Goldberg, who was at the University of Michigan from 1941 to 1960, promoted the wider availability of telescope and research facilities supported by public funding. The differences between these two factions created tensions that directly affected astronomers' plans to build bigger future telescope facilities. While in the post-World War II era, the public funding of science had become a reality, optical astronomy remained a poor sister compared to high-energy physics, rocket science, and other fields that had connections to national defense or later to space travel. Funding was available for large science projects for essentially the first time, but competition meant presenting compelling justification on a unified basis. This unified front did not exist in the astronomy community of the 50s and 60s. And there was no George Ellery Hale to bulldoze the next biggest telescope. But all was not negative in this period. When Sputnik went up in 1957, there was a movement to support science more aggressively, which led to the establishment of the United States National Observatory at Kitt Peak in Arizona in 1958. This facility has grown from modest beginnings to become the home of the largest collection of research telescopes in the world, 24 optical telescopes and 2 radio instruments. Providing open public access to all qualified professional astronomers for the first time. This action, the creation of Kitt Peak, which was supported and sponsored by the National Science Foundation, also provided the foundation for an ongoing public support structure for the development of astronomical technologies and facilities, as well as the operation of these facilities. While this new public structure for astronomy and its competition with the old private structure tended at first to thwart the decisiveness needed to support new giant telescopes, it did create a forum for discussion and debate which would eventually foster action as time passed and technology developed. Also in 1962, the National Academy of Science assembled a panel of prominent astronomers for the first decadal survey to assess the state of science and set goals for the next decade. These have continued to the present. Finally, a national framework for organizing resources and ideas to support bigger telescope projects began to be developed. With the forums provided by these new organizations and established older organizations like the American Astronomical Society, and with the natural march of technology in the modern world and in the space age, new ideas emerged, many of which were combined in 1979 in the multiple mirror telescope on Mount Hopkins in Arizona. More about the MMT in a moment. The first significant technical break with the past, however, came from the Soviet Union and their BTA-6 telescope, who in 1975 built the first major telescope to use an altitude azimuth mounting system controlled by a computer. While this 6-meter, 238-inch telescope had serious optical problems with its defective 42-ton overweight mirror, bad seeing location, and other design problems, its pioneering use of a compact, computer-controlled LTAS mounting system demonstrated this feature's practicality for very large telescopes. And this configuration has been used ever since in every giant telescope project. The great efficiencies of the LTAS mount would be demonstrated in later projects. The innovation spawned by the space race beginning in 1957 saw many technologies developing and becoming potential contributors to the future possibilities of giant telescopes. With the invention of the CCD in 1969, a rapid transformation of the field of astrophotography began, which continues to this day. The digital revolution in photography was in full swing during this period and had serious impact on the planning for future giant telescopes. The speed, capacity, and versatility of computers and microprocessors during this period was increasing at a breakneck speed, and its impact on the creative thinking with respect to new telescope designs grew to be profound. The Soviet BTA-6 telescope gave a dramatic demonstration of how precision control systems with computer guidance had evolved by 1975, so that a compact LTAS mount could achieve the precision tracking which previously had required a much bulkier, heavier, and costlier equatorial mount. In conjunction with more capable computers, better detectors, and improved systems understanding, many functions such as auto-guiding were becoming possible, changing the way astronomers practiced their craft. Finally, the engineering of telescope systems' mechanical and structure design was greatly aided by new advances in computer-aided design and simulation algorithms. At the heart of every large telescope is its primary mirror. This single component sets the parameters for the performance, size, weight, and very importantly, the cost of an overall instrument. The conventional design practices for casting these large parts reached their culmination with the 84,000-pound mirror used in the 1975 Soviet BTA-6. This massive solid hunk of glass, more than 23 inches thick, suffered from the distortions caused by internal thermal stresses, and its huge mass carried with it such thermal inertia that equilibrium was nearly impossible. As the decade ended, astronomers and telescope designers began rethinking the basics of primary mirror construction. We'll have much more on this later. Another emerging topic during this period was a growing interest in finding superior sites for the potential giant telescopes of the future. Up to this point, most large telescopes had been located on modest mountain peaks in California, close to major universities. In 1973, the 158-inch Hale telescope was christened on Kitt Peak at 6,880 feet elevation, and its twin, the Victor Blanco, at Cerro Tololo in Chile at 7,241 feet, thus establishing a precedent for finding superior locations for future major installations. Finally, In 1970, Fred Whipple from the Smithsonian Astrophysical Observatory, in search of an affordable way to build a bigger and better telescope, partnered up with the University of Arizona, where Aidan Meinl, the chair of its astronomy department and director of its Stewart Observatory, had been investigating novel concepts and telescope designs with faculty member Frank Lowe. Both had explored concepts and telescope designs and versions of telescopes that might combine the optical signals from several smaller telescopes into a much larger one. Meinl had secured 6 light-weighted 1.8 meter surplus mirrors from a canceled Air Force Spy satellite program, and Whipple had a prime location reserved at the Smithsonian Astrophysical Observatory on top of 8,600-foot Mount Hopkins, some 50 miles south of Tucson, Arizona. They successfully secured funding from Congress by wisely pitching the proposal as, quote, a large astronomical telescope at a low cost. Their efforts resulted some 9 years later in a revolutionary large telescope in which creative new thinking combined with newly emerging technological capabilities to bring high performance and cost efficiencies together for the first time in a major observatory. Its use of multiple lightweight mirrors to synthesize a much larger primary mirror, and its adaptation of a precision-controlled LTAS mounting which incorporated an integrated and compact climate-controlled enclosure, and many other innovations, initiated a wave of innovative thought in the astronomy community about the possibilities for future projects. The dithering period was finally ended, and the march toward giant telescopes had begun. The MMT had been built at a small fraction of the cost of the Hale, with comparable performance. 2 key aspects of its design made this possible: large, lightweight mirrors and the LTAS mounting. These aspects were in turn enabled by emerging technologies that were just becoming mature at this period: microprocessors, lasers, sensitive sensors, and advanced precision control systems and the like. Lightweight mirrors in this size range required a substantial change in mindset from classical mirror-making technology. Large telescope mirrors must deal with forces from gravity as a telescope moves to different locations, from vertical to horizontal. To mitigate sag and still maintain an exquisitely precise surface. Classic mirror design calls for the substantial structure inherent in thick sections of glass. This factor is represented by what is known as aspect ratio, the ratio of the diameter of a mirror to its thickness. The aspect ratio of classic large mirrors is from 6 to 1 to 10 to 1. The Hale is 9 to 1, while the Russian BTA-6 was 10 to 1. Resulting in massive weights of 29,000 pounds for the Hale, with its somewhat honeycomb structure, and 84,000 pounds for the BTA-6. Sparked by the success of the MMT, or the multiple mirror telescope, by the mid-80s, 3 competitive strategies for building large, lightweight mirrors emerged. 2 of these mirror systems were championed by creative individuals, while the third system emerged from the large corporate glass giants. I will discuss these still very competitive, back in the 1980s, these still very competitive systems in the 80s in some detail later, since they were at that time since they are now somewhat mature. But during the early 80s, all of these designs were hypothetical, then experimental, and then finally were all serious competitors for the various proposals for giant telescopes. All 3 designs were substantially lightweighted, although, as we shall see, this becomes a somewhat arbitrary matter because all 3 designs required an active optics mirror mounting support system. The degree of sophistication varies considerably between the 3. Active optic mirror support implies using electromechanical devices to provide shape-corrected forces as the telescope moves. With the promised new mirror technology, the astronomy community was awash with proposals for future telescopes larger than the Hale or the BTA-6. But the most focused and realistic program was for a 25-meter instrument called the Next Generation Telescope, or NGT, that was being studied by the National Observatory at Kitt Peak. In 1981 and 82, this program morphed into a scaled-down 15-meter telescope proposal called the National New Technology Telescope, or NNTT. Included the universities of California, Arizona, and Texas as partners. Since there was a major involvement by many influential parties, there were of necessity many meetings, committees, conferences, and politics played its inevitable role. A colorful part of this 3-year period of studying alternatives was a spirited presentation by Roger Angell and Jerry Nelson, each extolling the merits of their drastically different approaches for a 15-meter telescope. In July of 1984, the NNTT Scientific Advisory Committee held its final meeting in Santa Cruz, New Mexico, called by some of the attendees the Great Telescope Shootout, and selected Roger Angell's Arizona 4-shooter as a design to go forward. While this decision helped fund a much-needed expansion of Roger Angell's mirror lab at the University of Arizona in Tucson, funding for the actual building of the NNTT was not forthcoming, and this program was abandoned in 1987 in favor of a more modest proposal for several 8-meter class telescopes called Gemini. The NNTT program, it seems, had advanced the technology of giant telescopes, but not created the cohesive support of its members, who were all pursuing backing for other large telescope projects. Then, on January 3rd, 1985, Marvin Goldberger, the president of Caltech, announced the largest single gift ever made for a scientific venture. A $70 million grant from Howard Keck, son of a Standard Oil tycoon William Keck, to build a 10-meter telescope on Mauna Kea, Hawaii. Caltech partnered with the University of California, who had an active 10-meter program underway, using Jerry Nelson's segmented mirror system. The Keck, which was completed in 1993, ended the long dry period since 1948, when the 200-inch Hale became the first of the modern giant telescopes. It not only demonstrated the excellent performance of Jerry Nelson's brand new segmented mirror, but incorporated the weight and space efficiency of an Altaz mount and other contemporary technologies which became models for the several other giant telescopes which were in various planning stages by this time. The Keck collaboration of Caltech and the University of California also meant, though, that those institutions representing fewer than 5% of the astronomy community would exclusively share the observing time on the new giant telescope, with the University of Hawaii getting 10% of the time for hosting the observatory. This arrangement was a throwback to the earlier days of Lick, Mount Wilson, and Palomar. The world astronomy community, however, was taking note. Now that a successful giant was born, and now that several competing technologies for large, lightweight mirrors were potentially available in the early 90s, planning began for a number of 6.5-meter and larger telescopes. Several of these giants were nationally financed, like the Japanese Subaru or the American Magellans, but most were international consortiums and widely available to astronomers worldwide. We will review those telescopes later in this presentation. As these projects evolved in the early 1990s, two new technologies became very important factors to the field of ground-based astronomy and its sometime competitive nature with space-based astronomy for the support from the public and from the science community. These were technologies that had been closely held secrets by the U.S. military during the Cold War, and with the collapse of the Soviet Union, had become available and were important factors for astronomers in planning new major observatories. Adaptive optics is a technology that essentially allows atmospheric turbulence to be sensed and electronically subtracted from the optical path of a telescope. It does this by observing a target star, real or artificially generated, with a laser near the observed objects and analyzing its optical wave properties and generating a signal to a deformable mirror in the main optical path, which corrects the waveform of the light to that of a plane wave, thus yielding a diffraction-limited signal. All of this must take place at least 100 to 200 times per second and requires fast and significant computing power, which only became reasonably available in the mid-90s. The results with an adaptive optics system are dramatic, as shown in this slide. Yeah, there we go. Allowing large ground-based telescopes to achieve the diffraction-limited performance achieved previously only by space-based telescopes. Since the correction factor is more significant as the size of the telescope increases, it greatly enhanced the potential for every new giant telescope program. The second Cold War technology that became available to astronomers at the beginning of the 90s was the military's development of efficient infrared detector arrays, which complemented the astronomers' desires to explore that spectral domain with giant telescopes. Several of the programs that were being designed at that time were designed specifically to be optimized for infrared observations. As it turns out, measurements in the infrared domain are more readily and effectively corrected by the adaptive optics system because of the longer wavelengths involved. And so, as a 10-meter Keck 1 telescope saw its first light in 1993, the stage was set for a number of new giant telescopes to follow. But now let's take a brief look at what are the many considerations that go into planning a modern giant telescope observatory, as seen from today's perspectives. Some of these considerations were evolving in the late 80s and 90s when many of these giant telescope programs were underway. The first item, light-weighted primary mirrors, has been mentioned already and will be covered in more detail in the next section. So it will suffice here to say that three options now exist, and each has its own sets of pros and cons, and importantly, costs, which require consideration. As we shall see, all three options have been successfully implemented on more than one of today's giant telescopes. The second item, LTAS mounting, is also a given for all modern large telescopes, but many design variations come into play to meet functional or cost requirements. An example would be the Hobby Everly 10-meter telescope at the McDonald Observatory in Texas, in which the altitude adjustments are made by moving the secondary mirror assembly and thus sacrificing about 20% of the sky coverage, but saving a huge amount of money. Site selection is a major issue, involving a number of factors, most related to maximizing the opportunities for good seeing. Most of the preferred sites on modern observatories are at high altitudes to avoid as much of the Earth's atmosphere as possible. High altitude sites are also above most of the atmosphere's water vapor, making them ideal for infrared astronomy, whose wavelengths are strongly absorbed by water vapor. The preferred sites for the 16 giant telescopes built since 1993, when the Keck 1 came online, are in locations scattered around the world. 7 are located in the Atacama High Desert region of northern Chile, the driest place on Earth, with altitudes of more than 8,000 feet. 4 giant telescopes are now sited on Mauna Kea in Hawaii at an altitude of 13,600 feet. 3 are in the continental United States: Mount Graham, Arizona, 10,700 feet, Mount Hopkins, Arizona, at 8,500 feet, and at the McDonald Observatory in Texas. The 2 remaining giants are in South Africa and in the Canary Islands. Future giant telescope projects are aimed at either Mauna Kea or in Chile, if the Hawaiians will let them build the 30-meter. The next item on our consideration list has to do with the design of the telescope itself. It must have the structural rigidity to maintain the precise positioning of all the optical components relative to each other and to withstand external forces from gravity and the wind, as well as internal thermal expansion as the instrument heats up and cools down. This precise positioning must be maintained on a somewhat enormous machine, weighing hundreds of tons, which must move on at least 2 axes during its operation. These factors, combined with the efficient packaging of controls, instruments, and people, make structure and design a real challenge. The next important element is the creation of a house for our giant telescope. In earlier years, this would have automatically been called an observation or an observatory dome, but modern concepts take other shapes, predicated on factors such as the design of the telescope system and the need to optimize the interior and exterior climate while protecting the instrument from sometimes harsh environmental surroundings. One example is the MMT, or the multiple mirror telescope, which in its effort to maintain its big telescope for low cost promised to Congress, designed its enclosure to be integrated with the telescope mount and closely fitted around the telescope. The entire box-shaped, well-ventilated 460-ton building rotates in azimuth with the telescope. This was a space and cost-efficient solution to the limited space on the mountaintop. The next significant contribution to a modern major observatory has to do with the nature of the observations and the data to be gathered, and the detectors and analyzers required to achieve those goals. The basic design of the telescope needs to comprehend the types of instruments to be incorporated or used for data acquisition, how this data will be detected, stored, and disseminated. Modern detection and analysis technology systems are sophisticated, expensive, and rapidly changing, so it pays to keep on top of it. The next categories needed for a successful facility are interrelated because they often come from similar sources, be they private, institutional, or governmental. The cost for building a modern giant telescope observatory will, with a few exceptions, be into the $100 to over $300 million range in today's dollars. For example, the Kecks were $94.5 million each 25 years ago, while the Geminis were $184 million each. The Subaru cost a whopping $344 million. Operating budgets for large observatory complexes can be, if you will, astronomical, if you'll pardon the pun. The annual operation budget for the Gemini twin observatory system exceeds $20 million. Because of these large initial costs and ongoing operating expenses, most of these instruments and their facilities are funded by many international partners and/or institutions, usually universities. Using the twin Gemini 8.1 meter, 318-inch telescopes as an example, they are owned and operated by a consortium of 7 countries: the USA, United Kingdom, Canada, Australia, Argentina, and Brazil. Incidentally, comparatively speaking, the cost of space telescopes are truly astronomical, with the Hubble at $1.5 billion, not counting the 5 surface missions, and the James Webb at $9 billion and counting. The final essential element to build and operate a giant telescope observatory are a wide variety of people. For the design and construction, the talents of sophisticated engineers, opticians, instrument designers, and all sorts of specialists, contractors, and the like are all required and must be coordinated by a systems engineering management team capable for a very large and complex integration project. For the operation of a modern observatory, a rather significant primary technical staff is required to operate the telescope and its systems while observations are underway. Further technical staffing is required for data analysis, archival activities, maintenance, including mirror recoding, instrumentation, construction, maintenance, and IT activities, and the like. All of these personnel require food, shelter, and other services while on duty at often remote stations. Again, using the Gemini twin telescopes as an example, their total staffing hovers around 175 personnel. And this is just to operate the telescope and facility. Does not include the visiting astronomers or their customers. A competent manager is obviously required. And for those of you who are interested, go online. There are jobs available. I'd now like to go into a bit more detail about the heart of a modern giant telescope, its photon collecting element, the primary mirror. As I mentioned earlier, back in the 80s, there were 3 potential types of light-weighted large primary mirrors for telescopes under development, each distinctively different and each striving to become the preferred design for the upcoming new generation of giant telescopes. Remember, light weighting is the key strategy for giant telescopes mirrors, for reasons of mass, structural efficiency, and for fast thermal equilibrium. As it turns out, all 3 types of mirror designs have proven successful and are currently in use on a number of today's 16 giant telescopes. The 3 designs are shown schematically in this slide, which illustrates the drastically different approaches to solving the need for minimizing mass. Each of these mirrors should be considered as the main part of a primary mirror system, which also includes its mounting arrangements, as this may play a key role in its performance, mass, cost, and complexity. The first on our list is the meniscus mirror, which might be considered akin to a classical mirror in that it is produced as a homogeneous monolithic slab of very low expansion glass, either by casting, as by shot, or by fusing smaller slabs together, as by corning. Its main feature and means for light weighting is its aspect ratio, 47:1, as opposed to a classical figure of 6:1. An 8.2 meter mirror then is only 17.5 millimeters thick. That's 323 inches by 7 inches. It is very thin, a flat pancake, as some put it, like a gigantic contact lens, and as such may be thermally sagged to rough format. It is relatively flexible, requiring a complex active mounting system to maintain its shape. These mirrors are produced by several large industrial glass companies, Corning in New York or Schott in Mainz, Germany, and then figured and finished by outside optical firms. The second type of lightweighted giant primary mirror is the brainchild of Dr. Roger Angel from the University of Arizona. He has developed a process for casting mirrors of up to 8.4 meters in diameter, which incorporates a thin-walled honeycomb construction, making them lightweight, very stiff, and thermally friendly. These mirrors are molded in a rotating furnace which produces a thin parabolic top surface requiring minimal polishing, which is done in-house using an automated programmable procedure at their lab, underneath the football stadium at the University of Arizona Tucson campus. Some of you may remember my last year's presentation which described that lab. The focal ratio of these fast mirrors may be adjusted by changing the rotation speed of the large furnace. Final option in the choices for giant light-weighted mirrors called segmented and came up from the creative and determined mind of a University of California astronomer inventor, Jerry Nelson, who died only 4 months ago at the age of 71. Jerry overcame many obstacles in the quest to produce a system which allows for an array of somewhat smaller mirrors to work in concert as one large mirror. Since parabolic shape for such a system entails different aspheric figures or surfaces for each zone, there are 6 zones on the current 10-meter configuration. A new method of efficiently shaping each segment was invented called stress warp polishing. Other challenges involve the precise registration of segment-to-segment position and of accurately controlling the array's overall figure. This involves a very sophisticated mounting system for each segment and a comparably sophisticated computer control system to coordinate the entire system. Lightweighting, again, is achieved by using a relatively thin, very low expansion glass segments with an aspect ratio of something like 24:1, with current hexagonal segments being sized at 1.8 meter by 87 millimeters, or 71 inches by 3.5 inches. The cost of this lightweighting is somewhat offset by the necessary mounting provisions. It also should be noted that a cheap, an economical version, if you will, of the segmented mirror design is used on 2 current giant telescopes. These mirror systems use a spherical mirror in which all segments have the same spherical figure. I'll discuss these low-budget observatories in the next section of the report. So in summary, it is fair to say that the last 3 decades have produced 3 alternatives for producing primary mirrors larger than their venerable ancestor, the 200-inch Hale, which is still doing nicely, by the way. Each of these mirror designs has its pros and cons, which must be integrated into the overall planning for the construction and operation of a modern giant telescope. The more straightforward alternative, I would suggest, would be the spun-cast honeycomb, with its monolithic, lighter weight, high stiffness, and single-source aspects. However, it can only be produced and transported in sizes up to currently 8.4 meter, or 330 inches, kind of based on the maximum they can transport. The segmented mirror design, on the other hand, can be conceivably sized up, as we shall see, with limits imposed only by other considerations, such as cost and structural. The meniscus mirror, while slightly heavier, falls somewhere in between the other 2, being currently limited in size to just over 8 meters, and while monolithic, like the honeycomb, requiring a much more sophisticated mounting system because of its relative flexibility. Calculating costs for each of these mirror systems is kind of complex matter because of the interrelationship with other design considerations, primarily mounting, and because of the very competitive and passionate promoters involved. I'd now like to close out with a brief review of the 16 currently operating giant telescopes, those that fit my definition by being larger than the 200-inch Hale on Mt Palomar. All are 6.5 meter, 256 inches, or larger, and all use compact Altaz mounts, along with one of the light-weighted mirror concepts previously reviewed. I will describe them in order of size of their primary mirrors, which was shown on this excellent chart, with all existing giant telescopes shown to scale, along with several next-generation giants. And also shown here for reference are some other telescopes, notably the Hale, the Hubble, and the James Webb. You'll see them circled. The first giant on our list is the Large Binocular Telescope, or LBT. It is unique in that it has 2 8.4 meter, or 330-inch mirrors mounted to one Altaz mount, which may be used individually or coupled together in an interferometer mode, making it, by some definitions, the largest currently operating telescope in the world. It was commissioned in 2005, is located on Mount Graham, about 90 miles northeast of Tucson, Arizona, at 10,700 feet elevation. It belongs to various universities in the US, Italy, and Germany, and is operated by the University of Arizona. Its fast f1.14 focal ratio contributes to its compact design. The next giant telescopes were the first to see the light of day, or the light of night, if you will. The Keck 1 came online in 1993 using Jerry Nelson's segmented mirror design with 36 1.8 meter or 72-inch hexagonal mirrors, yielding a clear aperture of 10 meters or 394 inches, and a focal ratio of f1.75. Keck 2 is a clone of Keck 1 and first saw light in 1996. Both Kecks are owned and operated by the University of California and Caltech, with a partnership from NASA and the University of Hawaii, their hosts on Mauna Kea, at 13,600 feet elevation. The Kecks can be operated, although very seldom are, in an interferometer mode with a synthesized effective aperture of 14 meters or 552 inches. Fourth telescope on our list of giants is the Gran Telescopio Canarios, or GTC. Obviously Spanish. And my Spanish is not very good. Opened for operations in 2007 and located in the Canary Islands at 7,438 feet. This telescope was modeled after its earlier cousins, the Keck's, and as such has a segmented primary mirror with 36 hexagonal segments, but slightly larger than Keck's at 1.9 meters each, yielding a clear aperture of 10.4 meters or 409 inches, with a focal ratio of f1.65. It is operated as a partnership of institutions with 90% from Spain, 5% from Mexico, and 5% from the University of Florida, of all people. The fifth instrument on our survey of giants is named the Hobby Eberly Telescope, or HET. It's out near Fort Davis where the Texas Star Party is held. And it is notable that this observatory was built on a budget of only $13.5 million, about 15 to 20% of the other 10-meter telescopes. It achieved this goal by a simplified design with a fixed altitude mount at 55 degrees and an f1.8 segmented mirror using 91 1-meter segments, but with a uniform spherical configuration, since the telescope is designed for spectroscopic work and doesn't need as sharp of a focus. The fixed altitude mount and the spherical mirrors simplified the mirror mounting system and removed the need for an active control system, all of which resulted in major downstream structural economies. The telescope was built and is operated at the McDonald Observatory in West Texas, Davis Mountains, at 6,647 feet by the University of Texas, with partners at Penn State and several German institutions. The sixth telescope on our list, the South African Large Telescope, or SALT, is essentially a Southern Hemisphere adaptation of the Hobby Eberly that was just described. It uses the same f1.8 91 segment spherical mirror configuration and a fixed altitude mount down there at 53 degrees to achieve the economic efficiencies afforded. It began operations in 2005 at the South African Astronomical Observatory with partners from the USA, Germany, Poland, United Kingdom, and New Zealand. Next on our survey, number 7, and the size of its primary mirror, is the Subaru, Japanese for the Pleiades. This very sophisticated instrument, the most expensive of our giants, uses a monolithic meniscus mirror, 8.2 meters or 323 inches in diameter, with a focal ratio of f1.83. It permits measurements to be made from any of 4 focal points, including mounting an instrument at its prime focus, unusual for modern. This telescope began operations in 1999 and is owned and operated by the Japanese National Observatory. It's at Mauna Kea in Hawaii and has support from the Research Corporation of the University of Hawaii. The next 4 giant telescopes are owned and operated by a 16-nation consortium of European countries, along with Chile as the landlord, and are known as the European Southern Observatories, or ESOs, Very Large Telescopes, or VLTs. The ESOVLT operates as an integrated observatory complex, and as such, the 4 primary telescopes, along with 4 1.8-meter auxiliary telescopes, may be combined in various combinations as interferometers to achieve the ultimate resolution of 2 milliarcseconds, or the equivalent of a 130-meter telescope. Each of the VLTs is equipped with a meniscus-style primary mirror, 8.2 meters or 323 inches in diameter, with focal ratios of 1.75. The first of these telescopes came online in 1998, with the 4th and final one beginning operations in 2001. They are located at the ESO's Paranal Observatory in the high Atacama Desert of northern Chile at an altitude of 8,635 feet, which is, by the way, in the path of the 2019 total eclipse of the sun. Telescopes 12 and 13 on my list of giants are known as the Gemini North at Mauna Kea and Gemini South at Cerro Pachón in the Atacama Desert in northern Chile. Each telescope uses a monolithic meniscus-style mirror of 8.1 meters, or 318 inches in diameter, with a focal ratio of f1.8. Telescopes were built in '99 and 2000 and are operated by a partnership of 7 countries under the auspices of the Association for the Universities for Research in Astronomy. Number 14 on the list, and a telescope which I visited last May, is the renovated MMT, or now misnamed multi-mirror telescope, at the Whipple Observatory in Mt. Hopkins in Arizona, about 60 miles south of Tucson. You may recall from my earlier comments that the MMT was originally built in 1979 as a pioneer in modern large telescope design, using 6 1.8 meter donated mirrors to produce the first multiple mirror telescope in history, with an aperture of 4.7 or 186 inches and a compact Altaz mount, to build a large astronomical telescope at a low cost. At that time, it was the 3rd largest in the world. 20 years later, in 1999, this telescope was retrofitted with the first of Roger Angel's 6.5 meter or 256 inch spun cast honeycomb mirrors, while saving much of the original observatory. This F1.25 instrument is still owned and operated by the Smithsonian Astrophysical Observatory and the University of Arizona. The final 15th and 16th entries on this list of giant telescopes are the twin Magellan telescopes, located at 8,255 feet elevation in the high desert of the Atacama in Chile. This telescope project began as a single telescope using the second of Roger Angel's newly available 6.5 honeycomb mirrors. When it became apparent that a second 6.5 mirror could be cast for a little more than the price of one once the setup was done, the original partners, Carnegie, University of Arizona, and Harvard, then enlisted the University of Michigan and MIT to join them and built 2 F1.25 instruments, completing the first in 2000 and the second in 2002, and completing our survey of currently operating telescopes larger than the 200-inch Hale at Mt Palomar. I'd finally like to briefly review with you 4 near-future giant telescope projects that are underway and that will be operating in the not-too-distant future. 3 of these future giants are conventional, if you will, conventional design, but an order of magnitude larger than the current giants. While the 4th is only 8.4 meters, but significantly different in design, mission, and function. This slide also displays the scale of these new projects in several ways, impressively for any of you who have seen the Colosseum in Rome, I think. Of the future 3 mega-giants, the large Magellan telescope is well along in its development, with groundbreaking in 2015. The first light with 3 mirrors expected in 2021. At a cost of $1 billion when completed in 2025, it will sport 7 of Roger Angel's 8.4 meter spun cast honeycomb mirrors and have a 25.4 meter or 1,000-inch effective aperture with a focal ratio of f0.7. The LMT will be located in the Atacama Desert in Chile and is a U.S.-led project in partnership with Australia, Brazil, Korea, and Chile. The next larger program currently underway, the 30-meter telescope, has been stalled for several years over issues involved with protests by native Hawaiian groups regarding its preferred site on Mauna Kea. These issues should be resolved favorably by the end of 2017. There was a Supreme Court ruling recently about this. The TMT, or 30-meter telescope, is a project which evolved in the first decade of this century as a successor to the KEX from the same California heritage, with later partnerships from Japan, China, India, and Canada. It will eventually yield an instrument with a 30-meter or 1,176-inch f1.0 primary mirror made up of 492 1.44 meter hexagonal segments. It has an estimated cost of $1.2 billion. Its backup site, if the Hawaiian thing falls through, is in the Canary Islands. The final mega giant, and the largest of them all, is the Extremely Large Telescope, or ELT, which is under construction on a 10,000-foot peak in the Chilean Atacama by the 16-nation European Consortium, which runs the European Southern Observatory, or ESO. Construction started in May of 2017, and first light operations are expected in 2024. The telescope will have a 798-segment primary mirror with an effective aperture of 39.3 meters or 1,550 inches, and is projected to cost some $1.25 billion. I didn't mention it, but if you look on this chart here, this large circle that goes all the way around is a project that was abandoned here a few years ago. It's, you know, the other one's called the Extremely Large Telescope. That one was called the Overwhelmingly Large Telescope. For a different reason. The last future giant to be considered was given the #1 priority by the National Science Foundation's 2010 Decade Survey. And its construction is well underway near the Gemini South Observatory in the Atacama, with first light scheduled for 2019. It is known as the Large Synoptic Survey Telescope, or LSST, and it is billed as the world's most powerful camera, with its 8.4 meter, 330-inch spun-cast primary, a 3,200 megapixel camera, with a 3.5-degree field of view and a fast and efficient mount and guiding system. It will, in 2022, begin a 10-year program to continuously photograph the entire visible night sky, twice a week, with a detail and sensitivity never before matched. At a cost of $473 million, and with many technological firsts, it promises to be a headliner for the entire astronomy community because of its plans to efficiently share its data with all, including a major pitch to citizen scientists. That's us. We'll hear lots about the LSST in the near future. This finishes my survey. Finally, my presentation. Finally. But as usual, I'd like to leave you with a musical conclusion. Please sing along with me, and with my condolences to Matt Davis, for some of you who might remember. What's that? With telescopes you can't be humble. You look at things so far away. You need a big ear not to fumble, and you get better data each day. Your detector, it needs lots of photons from the galaxies way out in space. So you want a big scope to be spot on when you're in the astronomy race. At Yerkes, they had a refractor. Its big long brass barrel was cool, but the mirrors that were bigger and faster became the astronomers too. Now the size of some mirrors is astounding. They're so big they're not made in one piece. Like a big jigsaw puzzle, all those photons they guzzle from their homes high above mountain peaks. Oh, with telescopes you can't be humble. Join me now. When you look at things so far away, the bumble. As you get better data each day, your detector it needs lots of photons from the galaxies way out in space. So you want a big spectroscope to be spot on when you're in the astronomy race. And with telescopes you can be humble when you look at things so far away. I don't know if we have time for any questions, but I'd be happy to try.
At least two. Any questions for Jim? There's a question?
In one of your pictures, it looked like you showed where you're showing around the world where giant telescopes were. It looked like there was one somewhere close to the Middle East.
In China.
In China?
Yeah, there's one in China, but it's kind of it's a long story about that particular story. We can talk about it a little bit if you want to, sometime person to person. There's also one up in Canada. It's a rotating Mercury telescope that would fit into classification too. But I didn't think it was worth muddying the water or muddying the mercury about it. Back.
So actually, Jim, so I guess my question was whether there was a large telescope using a liquid mirror. Is that the only one in Canada?
That's the only one that I discovered in the research I was doing.
Okay, and my other question was, you said that the very large binocular telescope in interferometer mode is the largest optical telescope on Earth. But the Keck used to also have an interferometer that got shut down.
As do the VLTs of the ESO.
Say that again?
They can be coupled too. But the reason, and that's why when I mentioned the LBT, I said by some definitions is the largest telescope.
I see.
Because it is all on one mount. It's easier to do the interferometry. The other ones have to be synthesized and so on and so forth.
I see. So I thought I had heard that the VLBT was not actually being used as a unit anymore, that they were just using them as separate telescopes. Is that right? Or?
I think that's true. Although, in addition to the interferometric mode, they can use it looking at different parts of the spectrum at the same time, pointing it at the same target.
I think that's what I read, was that they stopped using it, or they weren't using it in interferometer mode very much because they were using it for multispectral stuff.
All of these telescopes that can be synthesized or coupled together can be using those modes, but they're very seldom used, as I learned, because it's very difficult to do that, and because it involves a lot of telescope time for specific purposes and so on. That's one of the reasons for the ELT, if you will.
Okay.
And these other ones, they expect to be using them more to get the resolution that you'll get with a larger telescope.
Okay.
And that takes us right to 10 o'clock.
Thank you very much.